Good morning. Welcome back to the transport phenomena class. So today we will discuss and do some exercise about how to use the equation of motions. Okay. So before I start, maybe do you have any question from last week? Any question? Hitungin dulu suara saya. Okay, can you hear my voice? Is it clear? Oh yeah, that means clear ya. Saya nyalain mikrofon saya. Oke. Ya, please. If you have any question, Zefania, please. But it's about the previous one, not the equation of motions. That's fine. Yeah, okay, that's fine. So what's your question? Maybe you can turn on your microphone and just speak here.
Okay, ma'am. I am wondering what exactly is defined as P, the P capital, the special P, I mean, because in the Bird's book, it was defined as the sum of pressure and gravitational terms. And in the case of the circular pipe, it was pressure minus rho g z. But in the quiz last week, it was defined as P plus rho gc. So I'm confused, like, is it plus or is it minus?
Okay.
Or does it depend on each cases?
Okay, I understand. So you read Bird, I think chapter 2.2 yeah, about the flow in pipe.
Yes.
Yeah, excuse me. So when you have this case, like the one in the Bird, yeah, the Bird says that, oh no, not like this. The one in Bird is downward flow like this, okay? And the Bird say that the modified pressure is P. I never remember this. I never remember what's the equations. Yeah, I have to do everything from the scratch. Is it plus or minus? I think this one is plus. Roji, is it?
Wait.
Zefania, yeah. I never remember what the sign because I always do everything from the scratch. Sorry. Plus. No, this one should be minus. This one should be minus, yeah. Minus Roji H or Roji 0, yeah. So basically birds, the one, so the description in birds sometimes leads you to memorize things, yeah. So this one makes you memorize that if you have downward flow like this and gravity on this directions, that downward like this, so the sign is minus, okay. But when you have upward flow, okay, because the gravity is still on this directions, so this sign will be positive. Yeah, basically the one in birds asks you to memorize this thing, but I never memorize things. Yeah, sorry, I never memorize things. So what I will say that if it is it plus or minus, it depends on the case. Yeah, it's depend on the case. So if you memorize things like this, you can do that, but sometimes when you have different cases and you have different 0-point coordinate, example like this or like this, yeah, sometimes it makes differences. Yeah, so I never memorize the sign and I always do everything from the scratch. Yeah, for example, if I have this, like downwards like this, okay, the pressure will always give me P0 minus PL. Okay, yeah, the one that comes, this one comes from the VZZ. I hope you still remember. Yeah, the VZZ, it has two components, the pressure and the rho VZ. Okay, because rho VZ in and out is similar, it's gone. Okay, so what we have is the pressure. And because we have flux momentum in minus flux momentum out, so the pressure is pressure in at 0 and pressure out. Okay, and if I have downward flow like this and the gravity is in these directions, means that the gravitational force or the hydrostatic pressure will give me rho g l. Rho gl, yeah, and it's positive. Why it's positive? Because I have this coordinate z to this directions and my gravity to this direction as well. Okay, so this one should be positive. So when I change this form, sorry, it should be like this, sorry, yeah. So when I change this form into the modified pressure form, okay, when I change this form into the modified pressure form, it will give me, I always write it like this, pressure 0 minus pressure L. Okay, rho GL must come here, rho GL, and the sign should be positive because it has minus, or it will be minus. Okay, minus, and on this part also should have minus to be to make it similar, and we have rho G0, which is 0. Okay, and then divide by L. Okay, so at the end I have modified pressure 0 minus modified pressure L divided by L. Yeah, so that's how to do that. Okay, I never memorize. Yeah. Okay, so if we have another case, in this case the flow is upwards like this. Okay, the flow is upwards, radius z, but the gravitational force to these directions means that what I have is I will have P0 minus PL. This these sections will be negative. Okay, will be negative because the direction is different. Okay, and then if I put to the modified pressure form, I will have P0 minus PL. Okay, and it should be minus rho GL. Rho GL should be here. It has to be minus, so I will put, sorry, it has to be minus, so I will put positive here. Okay, positive times minus will give you minus. Positive, put positive as well here, and this one rho G0 divide by L. At the end, I still have modified pressure 0 minus modified pressure L divided by L. Yeah, actually at the end we get the same equations, but what makes it different is the definition of the modified pressure. Okay, on this in this case the definition of modified pressure is positive sign, but for this case we have negative sign. Okay, so if you want to remember or memorize like once in the bird, yes you can, but just be careful. Okay, but if you don't want to memorize, you can do it from scratch like this. Yeah, it's easy. Okay, Zephania,
Okay, ma'am. And I'm sorry to ask again.
this is okay.
In the quiz answer that was posted by Burini last week,
I haven't looked at it. Sorry. Yeah. So what was it? What's in it?
I don't know, but I think it was written by Pak Danu, but the
Yeah.
cos beta was missing halfway. It was defined as GZ equals to G cos beta, but and then the GZ just disappeared halfway.
No, no, no. Should have cos beta. Should have cos beta.
Okay.
Yeah.
And also for similar case with the quiz, if we want to find force on the Z component on weighted surface, in the last week quiz, it was two plates, right? Instead of just one plate.
Yes.
Does it mean that we integrate the shear stress over the two plates area or just one plate?
Actually, you don't have to integrate, right? You don't have to integrate. You just need so to calculate the force. Yeah, the force. Yeah. So tau is force divided by A surface area. So the force is the momentum flux times the surface area, actually, So I cannot remember last week quiz, sorry. But maybe, is it something like this? Yeah, I think something like this. Yeah. So the fluid is flow upwards on to these directions between two plates, and I think it's considered as the closed system, considered as the closed system, because the thickness or the distance between two plates is so thin, so we can say that this must be closed system. Okay. Actually, you already get the momentum flux distribution equations. Tau is equal to something, 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 something. And then when you want to calculate the force, actually there are two force acting on this on the surface. Okay, the shear force here on the top surface and the shear force on the bottom surface. Yeah, I think this one is similar with when you have annulus. Do you still remember when you have annulus? Yeah, when you have annulus like this, yeah, and the fluid flows in between here. When you try to calculate the force, you have to calculate the force acting on this side, on this surface, and also the force acting on the surface. Yeah, so if you still remember the annulus problem, you have tau at, let's say this one is kappa r, kappa r times the area of the small cylinder plus the tau at R times the area of the big cylinder. Okay, so you have two forces two surface on which the shear force acts, this one and this one. And please remember, on this case, on this case, one of them is positive and one of them is negative. Yeah, the sign is different. Okay, so it's similar. On this case, you also have the surface. Yeah, on this case, you also have the surface because the surface is actually has a gap. Yeah, so it's not just one surface, but it is two different surface. Yeah, so if you want to calculate the shear force, so you need to. Oh, fortunately, the surface area of the top surface and the bottom surface is the same. So you have to do like this. Yeah, twice the surface area. Okay? Is it clear?
Okay, clear, ma'am.
Okay, thank you. Okay, more question? Maybe more question? Good? Okay. So now, matikan dulu microphone. Okay. Okay, now we're gonna move to how to use equation of change. I think last week you already tried to use equation of change with Bu Winnie using the case of falling film, the falling film case, the one when you have tilted surface and then there is a falling film on top of the tilted surface. Now we're gonna try to use the equation of motions to solve actually these problems. Yeah, the cylindrical problem. The cylindrical problem. This one. Okay. Do you still remember, or are you okay with using equation of change? Or any of you still confused on how to use the equation of change table? Good? Okay. If all good, so now just like the one we already discussed several weeks ago and just now, we have a cylinder and we have downward flow like this. Okay, we have downward flow like this in a cylinder, and now we want to know what is the flux, the momentum flux distribution, and what is the velocity profile of the fluid inside. Yeah, we're gonna try to solve this problem using the equation of change. Okay. Now, if maybe please show the birds B5 and B6. We're gonna use the equation in appendix B, table B5 and table B6. Yeah, I will share the screen so you can see the equation on your laptop. Okay, thank you. Can you please make it bigger? Like, yeah, thank you. Okay, now we have two tables. Okay, in tables B5 we can see equation of motions in terms of the momentum flux or tau, and on table B6 we have the equation of motions in terms of velocity. Yeah, so if we want to solve the first questions, what is the momentum flux distributions, so we're gonna need to use the table B5. Okay, because table B6 will be used to solve the second questions, what is the velocity profile. Okay, now let's look at the table. What we have in this case is not Cartesian coordinate, but what we have is cylindrical coordinate. So we're gonna look at table or equation B54 until B56. That's at the bottom of the screen. Okay. Now, if you look at those equations, clearly we have three different equations. Okay, we will not use all of that equation. Yeah, do you have any idea which equation are we going to use? No? Okay. So the one that we're going to use, if you look at the equation, yeah, equation B54, equation B54. When you look equation B54 and you look at the on the right on the equation on the right of the sama dengan ya. So you're gonna see tau RR, tau theta R, tau ZR. Right? Yeah. Actually, tau RR, tau theta R, tau ZR, and tau theta theta is all 0. Yeah, we don't have that component, so we will not use that equations. On equation B55, you can see we have tau r theta, tau theta theta, tau z theta, and so on. Okay. And on the third equation, B56, you can see that we have tau rz, tau theta z, and tau zz. Yeah. So in the cylindrical case, what we have is tau rz and tau zz. Yeah, if you still remember, yeah, what we have is tau rz, the momentum distribution to the r directions, because there is a flow to the z directions, tau rz, and also tau zz. So the equation that we're gonna use is the last equations, is equation B56. Yeah, so that's how to choose the equation. Yeah, you will in most cases you will not use all the equations, but tomorrow we'll discuss one cases, slightly complicated cases that will use all the equations. Okay, but in a simple problem like this, you will not use all the equations. For our cases now, the cylindrical coordinate, we're gonna use equation B56. Okay. Now, if you look at the equation B56, let's observe each term from that equation. The first term, dou Vz over dt. Yeah, dou Vz over dt. So dou Vz over dt is equal to 0. Why? Because what we have here is a steady state problem. Yeah, so dou Vz over dt is 0. The next term, Vr dou Vz over dr. Yeah, Vr dou Vz over dr. We don't have Vr. We don't have velocity to the radius directions. Yeah, we don't have Vr. So Vr is 0. Means that the second term is also 0. Okay. Next, we have, jangan dinaikin. Yeah, sip. Next, we have V theta over R, dou Vz over d theta. Okay, we don't have V theta once again, and then this term is also 0. The last part, we have Vz, dou Vz over dou z. We do have Vz, but actually the Vz is not changed. There is no change of Vz to the z direction. So dou Vz over dou z is 0. Yeah, there's no change of Vz to the z directions. So now we can see that the left hand side of that equation is all 0. Yeah, 0. I will write on the whiteboard 0. Yeah. Next, let's look at the equation on the right. Yeah, minus dou pressure over dou z. Yeah, minus dou pressure over dou z. Yeah, we do have the pressure difference over the length of the pipe. So we're gonna have minus dou p over dou z. Okay, next term we have 1 over r, dou over dou r, r tau rz. Yes, we have that. We have tau rz. Yeah, so I will write it here. Wait a second. 1 over r, dou r, r tau rz. Next term is 1 over r, dou over dou theta, tau theta z. We don't have tau theta z. Yeah, so that term is 0. Next, we have dou over dou z, tau zz. Okay, do we have tau zz? Oh, actually, we don't have. Yeah, we don't have tau zz. What we have is Vzz. So for the tau zz is 0. Okay. Now the last one. The last one we have rho gz. Yes, we have the hydrostatic pressure there. So I write it here. Okay. Boleh tolong kembalikan ke videonya, ke papan tulis. Okay, nah, so from that table we got these equations. Yeah, everything all good? All good? All good until you got these equations? No one confused? Or do you think like why that term is 0? Why that term has a value or thing? Are you okay? It's clear. Okay. Yeah. So finally we got these equations. Okay. So if we want to know what is the momentum flux distribution, we just need to solve this equation actually. Yeah. Let's try to solve these equations. You can move this part 1 over r, dou over dou r, r tau rz equal to minus dou pressure over dou z. Oh, this one is positive, sorry. Positive rho gz. Okay. Now, if you look at this term, this is the pressure changes over z. Okay, this is the pressure changes over z. Yeah. So this means pressure out minus pressure in. Actually, yeah. So this part actually is pressure out minus pressure in over Z out minus Z in. Okay, if you look at this, the pressure out here is PL, and the pressure in here is the P0 over L. Okay, now please note that we have minus here. Okay, so what we're gonna have when we substitute this to the dou p, we're gonna have P0 minus PL over L. Yeah, because we have minus here. Let's put minus here. Hope it's clear. Plus rho G Z, rho gravitational to the Z directions. Okay. Here we have 1 over R, dou over dou R, R tau R Z. Okay. R move there. I got dou over dou R tau R Z equal to P0 minus PL. P0 minus PL, and then want to put it should be rho G L. It should be rho G0. Wait, minus, sorry, wrong sign. Should be minus. It should be minus over L times the R here. Okay, now do one integrations. I got R tau RZ equal to modified pressure 0 minus modified pressure L over L integrations R square over 2 plus constant 1. Yeah, so what I got is tau RZ is over L times L divided by 2 plus C1 divided by R. Okay, yeah. So to solve this equation, we choose one boundary conditions. Boundary conditions at R equal to 0 or at the center of the pipe. You can say two things here. You can say either tau is finite, or maybe you can also say tau is 0. Yeah, why tau is 0? Because dou Vz over dou R is maximum. Yeah, maximum. That's sorry, dou Vz over dou R at this maximum velocity is 0, extreme point. Yeah, so the tau should be 0. This will give you constant 1 equal to 0. Yeah, constant 1 equal to 0. And finally, what you get is tau RZ is P0 minus, pressure, modified pressure divided by L times okay. So finally, this is the equation for your modified pressure. If you check on section 2.2, I think should be similar. Yeah, should be similar. Okay. Now, next. The second question is how to get the velocity profile. Yeah, how to get the velocity profile. If you do the shell momentum balance, to get the velocity profile, you have to do the tau first. Yeah, you have to do the tau first. You have to get the equation for the tau first. But when you use the equation of motion stable, you don't need to calculate from the tau. Yeah, I will erase everything about tau here. Yeah, I think this one is recorded. Yeah. Now let's see table B6 on bird. Okay, table B6. The one, yeah, next. Okay. Yes, thank you. Now let's look at table B6 for cylindrical coordinates. Yeah, just like the one in B5, we also have three equations here. Which equation are we gonna use? So to choose the equations, let's look our case. In our case, we have downward flow of fluids, means that the flow in z directions. Yeah, and because we have a laminar flow, means that all the flow is only to the z directions. We don't have the flow on the theta or on the radius to the radius directions. So because we only have Vz, we're gonna use equation B66. Okay, we're gonna use equation B66. Now look at the first term. Dou Vz over dou T is 0 because it's steady state conditions. Okay, next term Vr times something. We don't have Vr, so that term is 0. Next term, V theta over R, dou Vz over dou theta. Okay, we don't have V theta, means that term is 0 as well. Next term is Vz, dou Vz over dou Z. Yeah, we don't have the variation of velocity to the Z direction, so that term is 0 as well. So everything on the left is 0. Okay, next to the right. Dou pressure over dou Z. Yes, we do have that. Minus dou pressure over dou Z. Okay, next term, mu 1 over R, dou over dou R dou Vz over dou R. Yes, we do have that. Yeah, so the velocity to the Z directions will vary to the R directions. Yeah, there is a variation of velocity to the radius directions. R. Please wait, I have to write everything on the whiteboard. Okay, next term is 1 over R square dou square Vz over dou theta square. We don't have that because there is no dou Vz over dou theta. That term is 0. And next is dou square Vz over dou Z square. That one is also 0. Yeah. And last term we have rho Gz. Yes, we do have rho Gz. That's the hydrostatic pressure. Okay. So now let's go back to the whiteboard. Okay, so what we have from that equation of change in table 6, we have this. Yeah. So when we want to know what is the velocity profile, we just need to solve these equations. Okay. Now let's solve it. It's minus mu dou over dou R dou Vz over dou R plus, equal to minus dou pressure dou Z plus rho Gz. Okay. So for the dou P over dou Z, we do the same like before, like the one when we try to solve the momentum flux distributions. We're gonna have P0 minus PL divided by L plus rho Gz. Okay. Now if we have something complex like this, yeah, this one looks complex, like a very complicated equations. Yeah, to solve such complex equations, we need to be patient. Yeah, do it one by one, just like when you peel the onion. So now, first thing, move the minus mu over there. What we're gonna have is P0 minus PL minus rho GL minus rho G0 divided by L. Minus mu comes here. Minus mu. Okay. And then Do I miss something? Do I miss something from the table? Please wait, let me check, yeah, let me check. Mu, yes, I miss something, yeah, I miss something. Mu times, should be 1 over r over here. 1 over r, yeah. This doesn't look right, yeah. Minus mu, 1 over r. Yeah, I miss 1 over r from the table, sorry. Okay. Okay, so next move the r over there. That will give me minus modified pressure 0 minus modified pressure L time divided by mu L times R. Okay, do the first differentiations. R square 2. Okay, plus constant 1. Okay, next. The next thing is move the R over there. Dou Vz over dou R is minus modified pressure 0 minus modified pressure L divided by 2 mu L R plus C1 over R. Yeah, if you remember, actually this is the equations that we got from for the momentum flux distribution before. Yeah. Next thing is do the second differentiations. So if we do the second differentiations, we're gonna have minus, Vz is minus modified pressure 0 modified pressure L divided by 2 mu L integration R square. This will be 4 plus C1 over R gave us C1 ln R plus C2. Okay, to solve this equation, we're going to need two boundary conditions. Yeah, so the first boundary conditions and the second boundary conditions. Yeah, for the first boundary conditions, okay, so for the first boundary condition, we know at R equal to R, at R equal to R to the capital R, the velocity must be 0. Yeah, so by using the first boundary condition, we can see that, wait a second. No, we cannot use this one now. So for the second boundary condition, we know at R equal to 0 or at the center of the pipe, the dou Vz over dou R is 0. Yeah, because at the center of the pipe here is maximum velocity. So at R equal to 0, dou Vz over dr is 0. Yeah. So first thing first, we can put this here. Okay, when we put R equal to 0, 0, dou Vz is 0. That will give us that C1 is 0. Okay, C1 is 0. So now we put C1 equal to 0 here, and we get Vz is minus modified pressure 0 minus modified pressure L divided by 4 mu L times R square plus C2. Yeah, because the C1 is 0. Now we use the second boundary conditions. We put at R equal to capital R, Vz is equal to 0. Yeah, so 0 it gave us C2 modified pressure 0 modified pressure L equal to R square. Okay, finally from that equation we got the Vz is V0 minus PL divided by 4 mu L R square times R square divided by capital R square minus what? No, wrong. Oh, correct. Minus 1. 1 minus R square divided by capital R square. Okay, so this is our equations for the velocity profile. Question, okay, sorry. Sorry ya, to focus on the whiteboard. Okay, please, question. Wait. Okay. Sorry, Emma, can you repeat?
Oh, okay. For the C1, when we determine when the R is 0, is it supposed to be undefined then?
Here, at R equal to 0, here.
And we input that in the equation? Yes, because
Okay, so I understand. So when we put 0 here, yeah, let me change the R with 0, yeah. So this one R, I put 0 like this, and over here, yeah, I put 0.
Yes.
Correct? Yeah. Okay, something times the 0 will give us 0. Yeah, so I can erase this part. Yeah. So now we have dou Vz over dr. Dou Vz over dr is 0, yeah. 0 equal to C1 over 0. So how to get 0 is by determining that C1 is 0. Yeah, is C1 is not 0. For example, if C1 is 1 or 2 or other number, yeah, some other number than 0 divided by 0 will give us infinity. Is it? Or undefined? Yeah, something like that. Okay. But actually to get 0, we have to put C1 as 0. 0 divided by 0 is 0. Yeah. Okay. Is it clear, Emma? Sorry, is that what you asked?
Yes.
Yeah, okay. So if you put any number on C1 other than 0, it will give you infinity, undefined, something like that. Yeah. So you have to put 0 here. Maybe another question? Okay, no questions? Good. Okay, saya matikan lagi mikrofonnya. Okay, maybe if you don't have questions, you can do a quick exercise. Yeah, quick exercise. Maybe 10 or 15. What time is it now? Yeah, maybe 10 or 15 minutes, and then we will discuss the exercise, and then we'll go next to the we'll go to the next agenda, yeah. So for the exercise, maybe you can do this. Oh yeah, please, Fauzan. Yes, Fauzan, please.
Hello?
Hello? Hello? Yes, yes.
Okay, Miss. From the equation that you got from the Burst book, does that apply to the case where the flow is downward, right? So if the flow is upward, it will be negative for
Yes.
the rho g, right?
Correct. Correct.
Okay.
Yeah, correct.
Okay. I thought it was fixed. Okay.
No, no, it's not fixed, yeah, because it's vector, yeah. So you can change the negative positive sign, yeah, for the gravitational force.
Okay, Miss. Thank you.
Maybe more question? No, no questions. Okay. Maybe for the exercise, you can quickly do this, yeah. Now, suppose we have vertical pipe. Yeah, we have vertical pipe like this. And I have a fluid laminarly flow from these directions and out at this direction. Okay, it's laminar, it's Newtonian, incompressible, and so on and so on. Yeah, ideal conditions. Okay, the length of the pipe is L, and the radius of the pipe is R. Okay. Now, can you please determine what is the velocity profile? Yeah, what is the velocity profile? Okay, you can use the equation of table, the table of equation of change in. You can choose B5 or B6. You can choose, yeah, and then please try to get what is the velocity profile for this case. Yeah, okay, maybe 10-15 minutes, and then we will discuss it. Okay, finish. All finish. Have you finished? Any problem? Okay, maybe just discuss it. Okay, so from the equation of motion table, I got these equations, yeah, the blue one. Now I want to ask you, how about the gravity? Should be included in this equation or not when we have such case, a case like this? Anyone? No? Okay. No. Yeah. Okay, can I repeat? Okay, yeah. So from the equation of motions table, I got these equations, yeah, the blue one. Now my question is, should we include the gravitational force in that equation? Yeah, should we include the rho g from the equation? Someone, uh, Adrian, yeah, maybe I call it Adrian, yeah. Adrian and Emma and also Vanya say no. Yes, that's correct. So we don't put this equation, we don't put gravitational force here. Why? Because let's look here. It's GZ. So this is gravitational force to the to the z directions. And in our case here, our z directions is in this, it is to this directions. Yeah, means that there is no gravitational force to these directions. Yeah, gravitational force only act to these directions. So I erase the rho g, and up we have a very simple equation. Yeah, very simple. To solve this, maybe I quickly solve this. Okay. Now, because we don't include the gravitational force here, means that we will not our equation will not contain the hydrostatic pressure. Now we only have P here, yeah, the plane P, the pressure. We don't have modified pressure anymore because we don't have hydrostatic force here. Now, to solve this easily, dou Vz over dou R. Actually, it's similar to our previous equations, yeah, the one that I explained before, except that we don't have modified pressure here. Instead, we have just the plane pressure, the P over here. Okay. Now to solve, need two boundary conditions. So for the first boundary condition, at R equal to 0, dvz over dr is 0. Okay. And the second one, at R equal to capital R, Vz is 0. Okay. Yeah, you just need to put everything to the equations, and then at the end, I think you will get exactly the same equation like this, but you don't have modified pressure. You only have the plane pressure, just P. Okay. You can try. Is it correct? Can you do that like correctly? Yes, good. Good, yeah. Means that you already understand what is modified pressure, yeah, what is just the pressure, what is the hydrostatic pressure, and you also understand when to put gravitational force, when to not put the gravitational force, and you also understand how to use the equation of change table. Yeah, very good. Very good, thank you. Tomorrow we will have another discussion about how to use equation of change, equation of motions, particularly for more complicated cases that include rotational motion of the fluid. Yeah, so when you stir the fluid or when the fluid is moving in rotational directions. Yeah, so tomorrow we'll discuss when we have not so. Usually we only have phi z, yeah, to the z directions like upwards, downwards, and so on. But tomorrow we'll discuss when you have rotational directions. Okay. So I think for now that's all I can present to you. Do you have any questions? Oh yeah. Okay. Fauzan, please.
Okay, Miss. For the dp, is it PL minus P0 or P0 minus PL?
Oh yeah. Correct. If I put P0 minus PL, the minus should be gone, right? The minus should be gone. And then I got another minus from the minus mu. Yeah, so the minus comes again. Yeah, so it's gone here. Yeah. Okay.
And one more thing, Miss.
Yes.
If the gravity does not affect it at the z direction, will it affect at the r direction, Miss?
Yes, it is.
So, okay, Miss.
Yes, it is. So actually,
I tried to solve it using at the r.
Yes.
At the equation at the r side, but it doesn't work.
Yeah, it doesn't. It will not. Yeah, because you don't have a velocity. You don't have a momentum transfer. So what you have is the tau r z. Yeah, You don't, if you try to solve it to the and at the R equation, you got tau RR, yeah. I think you got tau RR, and you don't have this value actually, yeah. There is no momentum flux to the R direction because the flow to the R direction, because you don't have flow to the R directions, yeah. You only have flow to the Z direction on this case, yeah. So it will not work. But if you try to use the equation of motions, yeah, of motions that in the R directions, yeah, this one, you will get the rho gr, yeah, you got the rho gr, but actually everything is will be like 0 0 0 0 cancel out, so yeah, it will not work for the for this case. Okay,
Thank you.
you're welcome. Maybe any question, more question? No questions. So if you don't have any questions, that's all for now. But before we end this class, we have another quiz. Okay, so the quiz is in the Google Classroom. The quiz will be started at 11:30. Yeah, you can head to the Google Classroom now and prepare for the quiz. Yeah, the duration is 20 minutes, so you have to assign the quiz before 11:50. Okay. Thank you for now. See you again tomorrow. Bye.